Good afternoon, everyone. Welcome to the fifth webinar of AM Smart, Advanced Manufacturing of Smart Materials and Structures. We have another session related to the shape memory materials, advanced manufacturing, and in particular, additive manufacturing. The host of this session is Professor Thomas Niendorf from University of Kassel. Professor Niendorf has very nice experience on different type of shape memory alloys and also different type of advanced manufacturing processes. He's going to host this session with and welcome to two main speakers that we have. The interesting point about this session is we have two talks about different type of shape memory alloys and also different type of additive manufacturing processes. I hope that would be interesting also for you, but do not forget we record the session, and later on, if you are interested, you can watch it or share it with the other people who are interested in this topic. All right, thank you very much, and Professor Niendorf.
Mershad, thanks a lot for the introduction. Welcome to all from my side as well. It's my pleasure to host this event today, and we will have two very interesting topics that will be addressed by the two speakers Mershad already mentioned. The first speaker will be Christian Leinenbach from Empa in Switzerland, well known for his activities in iron-based shape memory alloys, and so this is what we will hear about in the next few minutes. The second speaker will be Philipp Krooß from my group in Kassel. There the focus will be different, but I will introduce him in a few minutes after the talk of Christian Leinenbach. So it's my pleasure, Christian. Thanks a lot for joining us today, for giving this presentation on a fantastic shape memory alloy, the iron-based alloy. I know what you do in terms of microstructure design. This will be one of the topics today, so I hand over and looking forward to a very interesting talk. Thanks a lot.
Thank you, Thomas. Thank you very much also for the invitation, and greetings to the audience from today sunny Zurich here in Switzerland. Yeah, my talk will be on the control of microstructure and shape memory properties of this iron manganese silicon based shape memory alloy during laser powder bed fusion. So this is a large teamwork. Basically, most of the results are from my former PhD student Irene Ferretto. We had partners in South Korea because this was a joint project between partners here in Switzerland, so us and Pusan National University, as you can see here from the funding institutions, and we also had industry partners involved. What I'd like to show you today, you can see here. I will give an introduction into how we can manufacture these iron manganese silicon based alloys, and then delve a bit deeper into microstructure control, microstructure manipulation, and give you just a few examples of what we can do with it in terms of making more complex parts. So the shape memory alloy systems, well, good thing I don't have to explain what shape memory alloys are to this audience, because I think most of the people are very much familiar with it. Here at Empa, we have been looking into shape memory alloys for quite some time with regard to the applications for civil or structural engineering applications. Here you see a bit what they do. We have different effects, pseudoelasticity or superelasticity upon mechanical loading and unloading, or the shape memory effect if we heat it, or constrained if we fix the material expand it in an extended state and then activate it, we can build up stresses. So this has been done for a while, but in combination with additive manufacturing, now novel possibilities are there. Fabrication of parts with hitherto unreached properties might be possible. Looking into the alloy systems that are around, most of the people are familiar with nickel titanium, but with regard to additive manufacturing, they're really difficult to process. They tend to cracking. There's a loss of nickel, and then they change their properties. So 0.1% of nickel can mean 10 degrees of difference in the transformation temperatures, so they're difficult to control. Another downside is they're really expensive, and in particular, when you want to make larger components, you cannot really afford that. Other systems that are known are these copper-based alloys. However, they have a fairly poor shape memory effect, are also very difficult to process. And then there's the class of iron shape memory alloys, or often denoted shape memory steels. They have been around for 40 years, and here at Empa, we've been studying them since 2006. In comparison to other alloys, they are fairly cheap and comparatively easy also to process on large scales, and they have been successfully used in civil engineering. However, before we started to work on several of these alloys, they have not been really studied in the context of additive manufacturing. Also, just here to remind the people, or those that are not so familiar with it, what we have done here at Empa. Well, we have developed a self-pre-stressing rebar. So you can see a bit what we can do. You can make plates or rebars, fix them in concrete structures, and heat them. And because they are constrained, so you can activate the shape memory effect, but they do not change their shape, but build up stresses as a result of that. And this is a novel approach used for retrofitting of civil structures, prefabrication of pre-stressed parts, and has been commercialized over the last more than 10 years by startup company, now not anymore here in Switzerland, Refair. And I just want to refer to a previous AM Smart webinar given by Professor Elias Gafori, a former collaborator and still good friend. So we've been working on this alloy for several years together. So for us, it was now rather natural to ask the question, can we 3D print this material? Just to remind the people how the shape memory effect works, that's a bit different from the nickel titanium alloys. So we have something that is more similar to a transformation-induced plasticity type of steel, so a trip steel. We do have a phase transformation, deformation-induced phase transformation from austenite, so FCC gamma parent phase, into a hexagonal phase upon loading. This is induced by the formation of stacking faults. And if we heat the alloy, then we have the reverse transformation from this martensite, this hexagonal phase, into austenite. So important here are the stacking faults. Please keep that in mind. We will get back to that at a later point. So we started to look into the additive manufacturing of the system now a bit more than 4.5 years ago. We decided to look into two variants of the alloy. They are basically the same composition, except that for one variant contains some vanadium and carbon for the formation of vanadium carbides upon heat treatment, upon an aging heat treatment, which does not only strengthen the material, but improves the shape memory properties. It facilitates the martensite transformation in our alloy. So here you can see a bit also what the powder looks like. We have done LPBF experiments on our machine, and to our surprise, we quickly had a set of parameters that allowed to fabricate dense, defect-free parts. And then afterwards, we had a look into, well, the microstructures, but also the thermomechanical properties, pseudoelasticity, shape memory effect, and different other properties. As everyone does in additive manufacturing, we look also for an effect of the build direction. So we also fabricated parts in different directions. Yeah, this is just the microstructure here as an example for the one without. That's the designation I'm going to use during this talk. We could fabricate dense parts. You see fine-grained microstructures. We have subgrain structures. And if we have a closer look by TEM, we could find very high densities of dislocations and also many, many stacking faults. And the characterization of the shape memory properties revealed that, well, our alloy, the additive manufactured alloy, performs better than the same alloy fabricated by conventional methods. So here, this is well, the pseudoelasticity, or in stress strain curves, loading, unloading curves, the hysteresis. So the dashed green line, that's the conventional part. And this on the right side, this is the free shape recovery, where we pre-strained the part to 4% and then measured how much of the 4% could be recovered upon heating and then cooling. So again, here you see the conventional alloy. You already see that there is an effect coming from the build direction, which I'm going to have a closer look now. If we look at the microstructures of parts fabricated in vertical direction or here in horizontal direction, we could see in the EBSD patterns that we have different textures, as it is indicated also by the reverse pole figures here. And we also see different grain morphologies along, well, in the direction of the loading, the external loads, if we do our thermomechanical experiments. Having a closer look at that, so this is just the stress strain curve where you see that horizontal parts, they have a higher strength but lower ductility, and the ones fabricated here in horizontal direction, no, vice versa, I was wrong, that's the horizontal direction, the blue ones, and the vertical directions shows a higher strength, more ductility, but also here, free recovery, vertical samples perform better, show a somewhat better performance than the samples fabricated in horizontal direction here. And that already gives a hint that if we play with the texture, if we manage to manipulate the texture, we can manipulate the shape memory properties. So this is due to the formation of the stacking faults. Stacking faults are the precursor of our martensite that we form. And having a closer look how textures affects the formation of the martensite, and in the first place, the formation of the stacking faults, we had a closer look at how does this now really work. And here we did some calculations. We calculated the Schmidt factors, which you often do if you have such phase transformations involved. However, here we looked into the Schmidt factors of the two components of a stacking fault, the leading partial dislocation and the trailing partial dislocation. And it's in fact that we see differences with regard to that. So on the right side, you see in situ EBSD images, so where we strained samples and then had a look at them under the EBSD. And we could see that we do have preferred grain families. I mean, preferred with regard to easy martensite transformation. And namely, here there are different examples taken from this larger picture. So we had the most pronounced transformation in this 101 or 2-to-1, this grain family, and apparently the weakest transformation in here when we are on the site in the 001. And if we have a look at the Schmidt factors, then we see it's in fact, if we take the difference between the leading partial and the trailing partial, so for the 2-to-0, there we have the maximum also difference. And this means if the leading partial, the Schmidt factor is very large in comparison to the trailing partial, then these stacking faults, they are opening up and can form easily then by, well, stacking of stacking faults, this epsilon martensite. So it's the 2-to-1, 2-to-0 grain family that seems to be very easy. 111 also, and it means if we have textures in the material, then we have more pronounced phase transformation, and as a result, we have a more pronounced shape memory effect. We could confirm that by in situ neutron diffraction experiments during tensile tests, where we looked into the evolution of the peaks. So here, this is the austenite peak. So for different grain families, 111, so the different ones. And you see also here that the 220 grain family, the austenite peaks with increasing strain decreases rapidly. So it disappears. And at the same time, we had a look into the evolution of the epsilon martensite peak. And also you can see that this is increasing at the same time. So this decrease is due to the formation of the epsilon martensite. This is true. The 220 family shows the highest transformation. And here we could then also look into the influence of the different build directions. So vertical versus horizontal. And there you see this is the epsilon martensite. The amount of epsilon martensite integrated intensity is a measure for the amount of that phase in the material. And there you see that in the vertical samples, we just had a faster and more pronounced formation of the epsilon martensite. And it's the epsilon martensite that is responsible for the phase transformation. So the more of it, then the more pronounced the shape memory effect will be. So texture is one influence. However, now looking a bit more into the processing and the influence of several processing parameters, we made some interesting observations for the two different alloys. So this shows the alloy without vanadium carbide. And here, two results. Here, this means high volumetric energy densities. And that also means we put a lot of energy inside, and the cooling rates in one melt pool is fairly low. On the other side, here we have lower volumetric energy densities, and the cooling rates are significantly higher because the melt pools are usually smaller and heat is dissipated more rapidly. And you see really a pronounced difference. Here I've just colored. Blue means we have a BCC phase, it's BCC delta. Green means FCC gamma. And we saw that basically we have more than 90%, 80-90% delta phase if we fabricate under these conditions. And if we change the parameters, this is inverted. We have mainly gamma phase, and you can also see here, this is very coarse grained. This is the typical microstructures that we know from LPBF. And here it's extremely fine grained material that was puzzling. If we look into our material with vanadium and carbon, so for also similar conditions, it's interesting. So here we also have very large grains. However, these grains turn out to be FCC gamma. And if we operate at higher volumetric energy densities, so again, we have a very fine-grained material, and occasionally we have these islands of BCC ferrite in our material. So this was really astonishing, having a look at what happens. Well, it's a steel, and in the steel, in particular these high alloyed steels, the composition can affect the solidification microstructure, in particular the primary solidification phase. So speaking in chrome equivalents and nickel equivalents, as a rule of thumb, if that is larger than 1.5, the material, the primary phase upon solidification is delta ferrite. If it is smaller, it's gamma austenite. So this is one thing. Our vanadium carbide, carbon is an austenite stabilizer, so we fall on that side, but I will get back to that. Then another factor, it's the amount of the austenite stabilizers, and in our material we have manganese, which is a volatile material, and we knew that from previous experiments that we can lose manganese, and we can control the amount of manganese that is evaporated. And with that, we can tailor the composition. And with the size of the melt pool and the VEDs in general, we can influence the cooling rates in our material. And this has another effect then on the phases that will form, mainly on the phases, on the phase transformations into solid state when we go further down in the temperatures. Because as you can see here, there are then transformations from BCC delta to FCC gamma. At high cooling rates, you can rush all the way through from the melt to the solid state and maintain the delta phase. And that helped us also to explain a bit more what we see here. So primary saltification phase of the alloy without carbon is BCC delta. At low VEDs, BCC is maintained because of the high cooling rate. At high VEDs, well, we induce the solid state transformation from BCC delta to gamma, which then forms this very fine-grained, mainly gamma microstructure. Here, our alloy, well, gamma is stabilized, so the primary saltification phase, because of the carbon, is FCC gamma. During the processing, we can lose manganese at high volumetric energy densities and then change these conditions. We can make it a delta solidifier. And again, like here, from in the solid state transformations later on, we can convert this BCC delta to FCC gamma at high VEDs. This has an effect or an impact on the properties. So looking at this alloy, so the one with vanadium and carbon, so we see for these conditions, we have fairly wide hysteresis curves. And this is the shape memory effect, so the free shape recovery that we observe. So it's fairly good. If we look into these conditions, there you see we have higher strength, higher yield strength. Our hysteresis becomes smaller, the pseudoelasticity becomes smaller, and the shape memory effect is less pronounced. And that led us also then to asking the question, so now apparently we can make shape memory alloys that, well, where we have good shape memory properties, but lower strength, and we can make very strong materials, but with less shape memory properties. Can we make something in between by now playing with the parameters? So we have two possibilities to play with the parameters. So one is, as we did before, varying the laser processing parameters, so the volumetric energy density, laser power, and scan velocity in the first place. And this we demonstrated here by just printing a chessboard of our shape memory alloy, making it in different regions either BCC or in other regions, as indicated here, FCC. So in all figures, BCC is blue and FCC is green. And there you can see also the impact on the grain size. However, in additive manufacturing, we also have the possibility to do rescanning. Means, so without applying another powder layer, just get back to a certain position and rescan that area before depositing a new layer of powder. And this is what we also did. So we started to write in our material with the goal that we deliberately evaporate manganese here. And as you can see here, SNF, these are the initials of Swiss National Science Foundation. So we could write in BCC phase in our primary gamma austenite phase. Then we took that further. Then we also said, now, can we make really 3D parts? So not just write some letters, but can we make parts? That's what we did, varying the processing parameters. We controlled the manganese evaporation. And there you can see that we can, depending on the pattern and what we imprint in our material, we can then make parts that vary their mechanical properties. Here's the stress strain curve, but that vary also in their shape memory properties. And here we can then make any combination in between. This just shows also the hardness value that you see. There is a pronounced difference between the gamma phase and also the delta phase. It also works by selective rescanning. Here we also made some samples where we produced distinct patterns in our part. So there we see, it depends a bit also on the spacing that we put, so the rescanning parameters. It just shows, so we can make really different structures, so like the ones that we have here. And we can not only play with the phases, as I showed you before, by tailoring the solid state transformation, we can also play with the grain sizes. And again, just by using this rescanning, we could make parts that showed differences in their mechanical properties, shape memory properties, and here that's a summary also of this. Also summarizing this, all parameters or properties at once in comparison with other alloy systems that we have found, conventionally manufactured iron manganese silicon shape memory alloys, and here in comparison also with others. Here's the recovery ratio versus the yield strength, so mechanical properties versus shape memory properties. And yeah, if I show this figure, I always say, well, for these type of plots, every time when you're somewhere in the top right, this means you're somehow good. And if I look here, it's somewhere top right, or at least center right. This means it cannot be too bad. Just rushing through, we can also make more complex parts of that, not just these zebra type structures. Here you can see that the shape memory effect actually works. So for this 3D structure, some also spiders that we produce that can lift weights, and also some lattices that we produced. And the idea now is also to take that further, to make such lattices or metamaterials where not only from the shape memory alloy, but yeah, with tailored microstructures, so that we can vary our microstructure and the composition in space, and with that have, yeah, new adaptive structures. Yeah. Just to summarize, yeah, this alloy, the iron manganese silicon alloy, is surprisingly easy and robust to fabricate by LPBF. The shape memory properties of AM parts are superior to those of conventionally manufactured iron manganese silicon alloys. And we can tune the microstructures. So that was a really interesting observation by tailoring the laser parameters, by rescanning. And I think this offers now novel, new possibilities for designing multifunctional components that can be fabricated by LPBF for a variety of applications. So I hope I was not too long, and maybe there's time for a couple of questions.
So, Christian, thanks a lot. That was not too long and absolutely impressive work. I always like to see that, what's possible in terms of direct microstructure design. So I can open this up now for discussion for the Q&A session. So to the audience, if you have a question, open your microphone and just talk. This is one option, or use the chat function to provide the questions in the chat. So Philipp Krooß already raised his hand and has now the first question at that point to start the discussion.
Thank you, Thomas, and thank you, Christian, for this wonderful talk. As we all know, additive manufacturing is a really nice technique to produce near-net shape products, and also, as you just mentioned, this microstructure design in this particular alloy. I have the question to the subgrain structures you mentioned in the beginning of your talk. Did this seem to be also connected to the additive manufacturing process, or so this is not found in conventional process alloys?
No.
So is this one of the reasons why you have this higher strength in the material?
Well, of course, it's more fine-grained. So you see also the solidification cells. This is certainly one reason, because as the hypothesis goes, it's more that it's the solidification cell structure that determines or that influences the mechanical properties. However, the shape memory properties, so I mentioned it also here and there, we found much higher densities of already existing stacking faults in our material. And we believe also they further influence also the mechanical properties and the shape memory properties, because they are the precursors then for also martensite that will form.
I see. Because I was asking, because we have different other alloy systems, which I will just briefly present, and then we also observed that the finer grain structure is not always bad for also anisotropic shape memory alloys. So it's sometimes it helps.
No, as I say here, it depends also on what you do. We have these textures, and we do see differences in the properties already here. So that is actually the first level of microstructure control or microstructure manipulation or property manipulation, if you want to say so. But this comes automatically out of the process.
It's wonderful. Thank you.
Good. Thanks a lot. So I see the next hand raised by Merschat. Merschat, go ahead. I don't see any question in the chat so far. So Merschat.
Yeah, thank you. Thank you very much, Christian, for presentation. It was very nice. But by the way, you already mentioned also to the audience, if you have any question, feel free to just add it in the chat, and then we ask the presenter on behalf of you. My question is about the process, because LPBF, the result you show, it was for the LPBF, and we already know the limitation in terms of the size for the things we manufacture with LPBF. Earlier, you also show some application of iron-based shape memory alloys for construction. What if we use different type of additive manufacturing process in case we want to make a larger structure? For example, in this case, maybe DED process would be something that we can take in look into that. Have you had any experience or something project working on that?
I don't, although we do have a DD machine, a beam machine, but we have not put the powder into that. However, Elias, he did one experiments, and so apparently it worked. They could fabricate the parts. However, the discussions that I also had with him is that the loss of manganese is much more pronounced because the melt pools, the melt pool lifetimes, they are longer. And I think this is something that is a bit difficult to control if you go for one wire arc additive manufacturing. DED, I think, yeah, we would have to try. I think it depends also on the size of the machine and the melt pool size. My main concern is really the loss of manganese. However, this is something that you could account for in the first place by just overlaying the material with manganese.
Okay, thank you. There is one question in chat.
So let's no, I don't see it, unfortunately. Merschat, can you read this?
Yeah, sure. We have a question from Ala, and she said, "Thank you for the presentation. Did the study include actual manganese composition after fabrication and rescanning to correlate with high wet and low wet, and how consistent this post-fabrication manganese percentage were?"
Yeah, thank you for the question. Yes, indeed, we did that. I refer to the papers that I have mentioned here on my slides. I gave the references, and yeah, all the things and the details are described also in the papers where we have measured. I don't know by heart what compositions we had, unfortunately, anymore, but it varied. So I think in these regions, we went down to 15% of manganese. But yeah, I would have to look it up again in Irene's thesis or in the papers.
Okay, thank you. Is there further questions from the audience? We still have some seconds, some minutes to have questions here before moving to the next presentation. No further questions. I would have more, but I can ask directly. Christian, go ahead.
Yeah, it's just also to the audience, please feel free also to email me after the seminar in case some more questions are coming up.
Thank you. So no further question popped up. Christian, thanks again for this excellent talk, for these insights, a fantastic system, and you gained really a high level of control over microstructure and so properties. Looking forward to the future results coming up. So now it will be the second talk of today's session. We will move to another system, well-known binary nickel titanium, but in this case, not the laser. It will be the electron beam that has been used for production of the parts. Speaker is Philipp Krooß from my group. He is the group leader for shape memory alloys and additive manufacturing, so a perfect combination, and will give some insights on recent results we obtained. You see some other names, but he will introduce the collaboration we have here at that point. Philipp, please go ahead.
So thanks, Thomas, for the introduction. So you took my introduction slide because you just introduced me. And thanks, Mershad, for organizing this nice webinar. And thanks to the audience for attending today's seminar. It's nice to see that so many people are still interested in additive manufacturing of shape memory alloys. I hope you can see my slide and hear me clearly. Today I'm going to present some, not the newest results of our group. It's about electron beam melting of binary nickel titanium shape memory alloys. And in this particular alloy system, we had an increased carbon content. You can discuss later why this was increased. And I will just detail on the impact on titanium carbides on some functional properties in this electron beam melted materials. This was a cooperational work from our group and from the Leibniz Institute for Solid State and Materials Research in Dresden, so Julia Rufenbach and Tobias Gussmann. It's not switching, why not? No. So again, my introduction slide. Thanks, Thomas. My name is Philipp Krooß, Group Leader, Additive Manufacturing and Shape Memory Alloys. I have an OSPIT profile if you would have to look on our previous research studies. I'm working at the Institute of Materials Engineering. Metallic Materials is the department. As Thomas just told, he's my boss, so to say. He's the professor here. Now he is standing in front of on this picture, in front of our electron beam melting machine. A few words on my person. I started my PhD in Paderborn. This was under guidance of Professor Hans Meyer, who's now in Hanover. And then I moved to Freiberg because Thomas Niendorf got a huge grant there. I followed him, so to say, to Freiberg. Was there for 1 year, continuing my PhD, and helped him a lot, I would say. And then from 2015, we moved to Kassel because Thomas became professor here. I followed him again. And since 2015, I'm now in Kassel, defended my thesis in 2017, and I'm still here right now. Okay, the institute is subdivided in 4 main groups, so to say, subgroups. It's first the residual stress and X-ray diffraction group. There we, as the name says, are dealing with residual stresses in different kinds of materials and also do a lot of research also on methodologies of X-ray diffraction analysis. Then the additive manufacturing and the shape memory group, where I am the group leader of, and then the structural materials, where we deal with fatigue and damage, mainly on structural materials, lightweight, high temperature materials, and some novel materials as well. These 4 groups are, so to say, interconnected via the idea to correlate between process microstructure properties and damage. So these groups are not separate in the institute. They are trying to cooperate, but we try to focus the topics in these 4 subtopics. So the idea is correlation between microstructure, process properties, and damage evaluation. As I said, I'm the group leader of these 2 groups, so the topic today will be for sure from these 2 groups. In general, we have a lot of SMA systems in focus. One of the main focuses is, I would say, the iron-based SMA systems, so iron-nickel, cobalt-based systems, iron-manganese, aluminum system, iron-manganese silicon system, the system just Christian talked about, and some high-temperature shape memory alloys like cobalt-based and titanium-based alloys, nickel-based shape memory alloys, nickel-titanium, which will be the talk from today, nickel-titanium hafnium, high-temperature shape memory alloys, and also recently we get a project on nickel and manganese thin magnetic shape memory alloys. Here we focus on multicaloric effects. Again, process versus microstructure, functional fatigue, and functional properties, also using in situ testing to get an idea what impacts the material performance, what is the detrimental aspect of certain alloys, and then try to improve the functional properties of these systems. And we also printed all these systems additively. So this is, we have it conventionally processed, we have single crystals, and now we move to additive manufacturing due to the reasons just Christian mentioned before, microstructure design and near net shape production. I think there's no need to go into much detail here. I would like just to introduce the shape memory effects very quickly. Superelasticity, stress-induced martensite transformation. When we release the load, the material transforms back to austenite. And what we in our group basically are focusing at is the functional degradation. So the accumulation of irreversible strain, sorry. So this means that the hysteresis curve may change as a result of cyclic functional deformation. And then in the worst case, you will have just an elastic material behavior after fatigue. Then the temperature-induced shape memory effects, I mean, all of you know these, the one-way effect and the two-way shape memory effect. We are also investigating in these materials, and as Christian just also introduced in the previous talk, the pre-stress effect, I call it pre-stress effect. It's the same, basically the same as the one-way shape memory effect. We apply a load, deform the material, release the load, then we heat it up, and then upon heating and cooling, we can generate a pre-stress, which can be used for different applications. This is a picture from Refer. They work together with the Empa, and Christian was one of the inventors of these pre-stress applications. This works very well, and it's very successfully applied in industry for rehabilitation of bridges and buildings. Okay, this is a very busy slide. Just to quickly introduce to nickel titanium alloys. It's a different form of transformation than in Christian's alloy before. Here we have now the B2 austenite transformation to B19 prime martensite, as is well known for nickel titanium. Applications are mainly seen in the medical sector for stents, for example, but also increasing applications are seen in the automotive and aerospace sector, as the NASA is very successful in approaching for these systems. Also, Impulse in Germany is applying a lot of research and new applications in the automotive sector. High biocompatibility, highly deformable, and high weight specific power capability, high energy density, which holds true for most of the shape memory alloy systems. But in this case, the high biocompatibility also opens up this medical sector in this alloy systems. But from our point of view, since we are dealing a lot with other shape memory alloys, nickel titanium is quite complex in its manufacturing routes. So there are systems that are easier to manufacture. They are very sensitive to changes in the chemical composition. This also holds true for a lot of shape memory alloys. We all know this graph from Frenzel et al., where the nickel content is plotted versus the MS temperature. And also we have a very high sensitivity to carbon and oxygen in these systems, because it's always also changing the transformation temperatures upon a different level of carbon or oxygen. So it impacts the structural stability and also the functional, so the reversibility. So AM, we do it, as I said before, for near net shape production, and also, as we just learned from Christian's talk, for microstructure design. Here's a famous picture from Professor Niendorf from 2016. It's a structural steel, but basically it's the same. We can go for highly textured microstructural areas and for finer grained, and then we can switch the properties. This is the same topic which Christian just told before for this iron manganese system. Coming to the electron beam melting process, this is quite different to the selective laser beam melting process, because we have an additional step we need to think about. So basically we apply a powder layer. So we have a CAD file, we apply a powder layer, then hatch the components and lower the build plate. It's the same as the SLM process, but we need to preheat the powder bed, because we cannot melt the loose powder. We need to sinter the powder, pre-sinter the powder, to avoid the risk for powder blast. Yeah, so, and then afterwards we can sandblast the material, which is a kind of sinter block where the part is inserted. And then after sandblasting, we can get rid of the sintered powder and get the component. You can see a video. This is now the preheating sequence. So the powder is preheated, pre-sintered, and we can raise the temperature in the chamber. And then the electron beam is very fast. Now it's melting the material. And in between, you see these lines. It's still heating the material. And the electron beam seems to be everywhere at the same time. This opens up different possibilities. Powder blast, just really quickly, is basically the charge of the electron beam hits the loose powder, and then the powder cannot transmit the charge of the electron beam, and then the powder basically explodes, and this means then cleaning up the machine again, setting up everything new. It takes 1 day cleaning all the machine because the powder is sitting in the cathode in every corner of the machine, so it's very annoying when this happens. So very important to pre-sinter the powder. This is the machine ACAM A2X we used for this particular story. The process takes place in a vacuum atmosphere with a partial pressure of helium. The build plate temperature in this case was raised to 920 degrees C. It can be higher in other alloy systems, but in this case, 920 seems to be a good temperature for pre-sintering the powder. Then beam current, scan speed set up to 5,000 millimeters per second, etching distance 0.15. And maybe one important thing, we use for the electron beam melting process a larger powder fraction. So SLM is mainly for 20 to 60 micron. Here we use 15 to 150 micron. So it's always good when we order powder, we can use it for both processes. All in all, this results in an energy input of 24.6 joules per cubic millimeter. Okay, coming now to the science part of the talk, we first analyzed the powder. At the as-cast material before, I should start with the as-cast material because the as-cast material already showed some increased carbon content. And upon processing, powder processing, the carbon content was increased in addition, so doubled, 0.2 weight percent. This is due to the Vega process, which was used at that time. But in general, the powder looks not bad. We have the majority is spherical of the powder particles. Then we have some non-spherical particles, some banana-like particles. Also, we have some satellites here and some hollow particles, but this is nothing really special. This can happen to powder, and I think every powder has such defect. What we then observed in the cross-section of this powder, we see already these titanium carbides within the powder particles. So because of the higher content of carbon, we already have this carbon content in the powder, and then we try now to process this powder. One thing I need to mention, during processing, because it's in a vacuum chamber, and during processing from the as-cast, so the whole production range, we lost about 2% of nickel. So in the as-built state, it's only 48.8 or 48.9 atomic percent nickel coming from 59 around. So 2%, approximately 2% nickel loss during the whole process chain. So now coming to the microstructure. First of all, we had a pretty dense microstructure above around 99.9 density. And when we look at these EDS mappings at different scales, so this is the 5 micron scale bar, this is the 100 micron scale bar, we found these titanium carbides within the matrix being around 1 micron to 10 micron in diameter or in size. So different size fractions of the carbon was found here. And but we could not observe any further oxygen pickup. This makes sense because it's a vacuum process, so to say, that there's no further oxygen pickup due to processing, which could happen in, or maybe is more reasonable that it happens in selective laser melting processes. Then we looked at the phase composition just to be sure what's going on there. And obviously the titanium carbide was not present in the diffractogram, maybe due to size and volume fraction, because this very finely dispersed. Maybe the volume fraction was not enough to get it in the diffractogram. And we were a bit surprised that the austenitic condition is fully austenitic, so no precipitates was found in the material. Normally nickel titanium is full of some precipitates, especially nickel-rich nickel titanium. And but in this case, it was pure austenite after printing. An explanation could be, although this is not really true, because this is an isothermal TTT plot, and I plotted the cooling path of the EBM process. But it just should give a hint what happened in the microstructure. So the cooling path, so the process temperature was 920 degrees, and the cooling path is plotted here. So the process stops, the machine cools down. This takes quite an hour or something, and then I just estimated the time we spent in this Ni4Ti3 regime where these precipitates can form. It's only 12 minutes, so we suggested that there is no precipitation in the material, and this is the reason why we cannot find it in the diffractogram. When we then do some solutionizing and aging and do this diffractogram again, we can see this Ni4Ti3 precipitates, very small peak here in this region, so the material behaves as it should in terms of aging. having a deeper look into the microstructure, we found out that we can see the titanium carbides in both conditions, although we did not see them in the as-built diffractogram, but we can see it in the TEM. So these are around 5 micrometers. We have just found here some titanium carbide in the as-built condition, and the rest of the matrix is totally B2, no precipitate, no other phases present here. This is flip lamellar. You see these very small carbides, and in between there's also not much space. And when we do aging, we found out that here is this nicely precipitated Ni4TR3 phase, also proof with this TM analysis. So the TM results supports the XRD results, no precipitates in the as-built condition, but Ni4TR3 precipitates in the aged and solutionized condition. So does anyone get the mistake? In the beginning, I said we lost 2% of nickel. So how can this Ni4TR3 precipitate build? This shouldn't be possible because we need a nickel-rich composition in order to be able to form this Ni4TR3 precipitates. So we just, when we wrote the paper, we were just arguing what could be the reason for this. And we finally came up with an idea. It's an assumption or a suggestion that the titanium carbides, because they are very finely dispersed in the matrix, lead to a very complex chemical composition. And this means that the carbides or the bondage between titanium carbide leads to a depletion of titanium in the matrix, and this leads to an increase of nickel. And then we are again nickel rich in some local areas in the matrix, which then allows for the precipitation of this Ni4TR3 precipitates. Yeah, up to now, nobody argued with us. So this is now the truth we can tell here. So the carbides has an impact on the precipitation behavior, and with this we can then manufacture highly carbon content nickel titanium alloys, which show some nice functional properties, which I will show in a second. Just a quick look before I do this on the microstructure. As expected, due to the electron beam melting process, we got a very high columnar or strong columnar grain microstructure. In the as-built status, we have a pretty high texture index as well. After aging and solutionizing, this increased a bit, but this could also be just a sample-to-sample variation. Anyhow, we have a really high 001 texture in these samples, very long columnar grained microstructure. And according to this inverse pole figure plots, where we can see the strains, which is calculated by the energy minimization theory, we will expect some 5 to 6% reversible strain in such a microstructure, only due to the texture of these materials. And when we now look at the superelastic response in this material, we already found in the as-built microstructure a pretty high stresses, unusual high stresses, I would say, for nickel titanium, but a very good reversible functional response here in the hysteresis. Upon aging, makes sense. The critical stress for transformation stress for metallic transformation decreases a little bit due to the presence of the precipitates. They have some stress fields surrounding, some coherency stress fields, and this allows for very nice and smooth, highly reversible superelastic hysteresis here after solution treatment. Obviously, we would like to have this because we would like to process near-net-shaped materials. There is some way to go for with this as-built status, but anyhow, we could get very nice hysteresis out of this highly carbon content material. We also did some cycling, only up to 100 cycles. I know this is not really representative for any application, but at least we did a test, and we saw that there's almost no functional degradation in this material, so it seems to be stable as well, which kindly, or which so to say, is not really in context of the literature, because these titanium carbides always are shown to be detrimental for the reversibility of nickel titanium. Okay, just to quickly sum it up, before I have some other slides to show to you. So we were able to process this material. The titanium carbides seem to be dominating the microstructural evolution, and then basically, due to the nickel loss, allow for the precipitation of the Ni4TR3 precipitates, and we obtained a really nice superelastic reversibility. Next steps we would like to do, before we need to get some more powders, but what we do is we like to further adjust the process parameters to get the as-built condition more functional, more reversible. And we will surely go for some functionally graded materials, the same idea which Christian has on the iron-based SMA system. And we for sure will go for actuation response and the tensile, also on a tensile load, because the results I showed here was only on compression. And we started already to adding some ternary elements, so going for the high temperature SMAs by addition of hafnium. And this is just what I wanted to show briefly. This is a paper we are currently writing. We did a 5x5 matrix of process parameter development, and all these parameters were, not all were 100% dense, but 99.4 to 100% dense. 100% is need to be set carefully, but we had a very high density in these materials, very nice and strong textures, and very nice reversible response. And the volume energies we ranged here was 10 joules per cubic millimeter to 216. This was quite surprising for me, because I would not thought about this. Such a huge volume energy range is feasible in these alloy systems, but we are on it. Paper will be published in a couple of months, I hope, and then I can surprise you, hopefully. Before I end, I have 2 minutes, I guess, 1 minute. Before I end, I would do some advertisement, not only for me or institute, also for Thomas Niendorf, because he's the major investigator of this. Thomas applied for a DFG major instrumentation initiative. It's a DED machine with a high energy X-ray source. So basically, we have a DED machine which can print different kinds of structures, but basically we're interested in printing walls. And we have a metal jet X-ray source, which is a very high, strong, so to say, synchrotron, laboratory scale synchrotron in front of a DED machine. And we would like to use this machine for diffractometry during the process, for radiography. So look at the melt pool turbulences, and so radiography, phase analysis, texture analysis, some different additional instrumentation which can be applied to the system to get a whole bunch of informations of the solidification processes in the system on different alloy systems. We have powder and wire processing capabilities. We have an 8-feeder system, so we can basically, or we will have 8-feeder systems later on for feeding 8 different powders, so to say, and we can then print materials libraries and go for alloy design. And this is not the end. So the machine is just delivered, and we're just setting up everything, and we are open for external usage. This is common for the DFG, so everybody can apply for some beam time, so to say, in our institute. And if you're interested, let us know. Come to Kassel, visit us, and use this wonderful new machine. With this, I would like to end, and thank you for your attention.
Oh, thanks, Philipp, for this great introduction of our most recent results and for the advertisement of that machine. We are running almost out of time. I need to ask Mershad if we still have the time to have the Q&A, or should we stop here and have all the
maybe we can do an answer to a couple of questions. If anyone has a question, just raise a hand or write it in the chat.
That's a question in the chat.
Yeah, I can read it for you. Thank you for the great presentation. I was wondering if you encountered any challenges related to powder delivery spreading during the preheating stage, specifically regarding the adverse effect of temperature on the powder's spreadability.
Okay, you mean if the preheating stage affects the spreadability of the powder?
Yeah.
I think then when you preheat the powder, it's sintered, and then you apply then basically the next layer powder, and I think there's not a huge problem. For sure, defining the process parameters in electron beam melting is, from my point of view, much more challenging than in selective laser melting, especially due to this preheating sequence. But in particular on the spreading of powder, I have no information that this is especially a problem. So I don't think so, no.
Just to add, the machine is designed for that, and the powders in the storage tanks are not heated up to that level, and so this is already addressed in the machine design.
Yeah.
Mm-hmm. Okay. And maybe I can ask one quick question. What do you say if you compare LPBF and EPBF for printing a material like binary NiTi? What is your observation?
So we didn't print nickel titanium in LPBF by now,
Okay.
so maybe I'm the wrong person to answer this. But since I know these processes, both I would suggest that the high temperature in the EBM process, so 920 degrees C in our case, is beneficial for printing shape memory alloys.
Mm-hmm.
It's so the microstructure changes significantly, and I think this high temperature opens up a possibility of printing hard to print materials. So I think the formation of cracks, for example, is a less issue in electron beam melting than in LPBF. And this is one big advantage of this process, although it's a bit more complicated. But I think this is the great advantage of this process.
Okay, thank you. There is one question here, and thank you for your wonderful presentation. Could you please explain the mechanism of formation of Ni40I3 precipitate? How was this confirmed?
Okay, it was confirmed by diffraction of in the TEM. So we cut a small lamella via focused ion beam from the sample, and then we moved to the TEM, transmission electron microscopy, and then we did some diffraction on certain areas, on certain orientations. It's temp technique. You need to look at the orientation on which plane the precipitates form, and then you do diffraction, and you can prove that there is the presence of precipitates in this particular plane. There are books like 1,000 of pages where you can look up the planes you need to look at in different crystallographic structures, and then you can prove the precipitates are present or not. So TEM is the method you should use here. Also, atom probe or other techniques are usable, but TEM is, I think, the most common technique to show the precipitates, also the size and the morphology and the coherency and every particle that is important. I hope that answers the question.
Yeah.
Oh, is there further questions? I always have here a slight delay in the chat, but
not anymore.
No more questions. So I think it's time then to thank both speakers for their excellent presentations. Thanks to the audience for attending, for having the questions. As already said by Christian before, if there's any further questions, just contact us directly or via Mershad. So we will then provide answers on that. And yes, thanks from my side. I will hand over to Mershad for the final words.
Thank you, Thomas. Thank you very much. Thank you, and also Christian and Philipp, for your very nice and interesting presentation. Just only one point I would like to add. I also mentioned it at the beginning. The video of this session is recorded, and for you, if you want to see it later, it would be available on the LinkedIn of the let's say this webinar. Then I would request to follow that. I mean, follow our LinkedIn page, not only for this, also for future webinars. The next one going to be in November and will be hosted with a colleague from Ireland and two nice speakers from Germany and Italy. You will be updated about the information and also topic later. I would like to thank you all for presenting and attending this session. Thank you.
Thank you, Mershad.
Okay, have a good day.
Thanks a lot.
Bye, everyone.
Thank you. See you soon. Bye-bye.
Bye-bye.